Mr. Carlson here. Let's talk about ions and ionic radius. And really, in order to talk about that, we first have to go back a little bit to last week and remind ourselves about one thing that we learned about, which was the atomic radius. When we were talking about atomic radius, what we were essentially talking about was really the size of atoms. The size of atoms. And we saw some general trends within the periodic table when we were looking at the sizes of atoms. We saw that in general, for the atomic radius, or the size of atoms, as we work our way across the periodic table, so here's my general outline of the periodic table, not drawn to scale, obviously, but if we're working this way across the periodic table, across a group, we would see that the size, or the atomic radius, of atoms generally decreases. Generally decreases as we move across a period. So if I move across period 1, which has hydrogen and helium, I would see that the size of helium is actually a little smaller than hydrogen. And remember, we said that's because as we move this way, we gain some protons, and therefore there's a little bit stronger of a pull on those electrons towards the center, and so it makes the size of the atom a little bit smaller. But as we move this way, so down a group, we see that the atomic radius, or the size, actually kind of increases. Will increase, and we said the reason for that was because as we move down a group, as we move down the group, those energy levels get further and further away from the nucleus as we get farther and farther down, and so therefore the sizes of those atoms starts to increase. So that's the general trend when we're looking at atomic radius. So for a neutral atom, that's the trends in size we see. But what about ionic radius? And heck, for that matter, maybe you might be asking yourself, what is an ion? Well, I'm glad you asked. Let's answer that question. An ion is basically whenever we have a neutral atom that either gains or loses electrons and becomes charged. It gains a charge. Whenever something gains or loses electrons, it's going to get a charge to it. It's either going to be positive or it's going to be negative. But when that happens, it is now no longer a neutral atom. It has now become an ion. For example, let's say we take magnesium. And I'm just going to draw the electron dot structure for it, which shows the valence electrons. Magnesium, let's see if we've got the periodic table. There it is. It's got drawn all over it, but that's all right. Magnesium is right here, okay, and it is in group 2. Therefore, it has 2 valence electrons. We learned that last week. So I'm just going to put 2 dots here showing magnesium's 2 valence electrons. Now, magnesium is not very happy with just 2 valence electrons. In fact, we're going to find out that most or all atoms really want to get a full outer shell of 8 electrons typically. Some of them will be happy with 2, but we'll get to that in a little bit. But most of them want 8 electrons in that outer shell. Magnesium only has 2. And so typically what magnesium will do is it will get rid of these. It will just lose them, and it will give them to another atom. And again, we'll get more into that in the next chapter, but for right now, let's just understand the fact that magnesium will typically get rid of those 2 valence electrons. And when it does that, let's think about this. Magnesium, let me come back to the periodic table here. Magnesium has 12 total, right? 12 total protons and 12 electrons. If it loses 2 electrons, but still has 12 protons, so it still has 12 protons which have a positive charge, right? And it had 12 electrons, but then loses 2 of them, so now it only has 10 electrons which have a negative charge. That means the overall charge of this magnesium ion now, it has now become an ion, because now it has a charge of +2, doesn't it? Because it has 2 more positive charges than negative charges because it got rid of those negative charges. It lost those 2 electrons. And so the way we would write that is we would put Mg, and we're going to go 2 plus up here in the corner. That is how we would write the symbol for a magnesium ion, Mg2+. Let's think about a different one. What about fluorine? Fluorine, if we look at the periodic table, is way over here. Here's fluorine. It's in group 17, which means it has, I'll let you think about it for a second, group 17, how many valence electrons? How many valence electrons it has? That's right, 7. So I'm going to put 1, 2, 3, 4, 5, 6, and 7. Now, same thing with fluorine as it was with magnesium. It wants a full outer shell. It can fit 8 in this valence shell here. It can fit 8. So what's fluorine going to do in order to gain its stability to be like magnesium? Magnesium got rid of 2 electrons. What fluorine is going to do, it's not going to try to get rid of these valence electrons. What it's going to do is, since it's already got 1, 2, 3, 4, 5, 6, 7, it just needs to get one more in order to get that full outer shell. And so what fluorine is going to do is really the opposite of magnesium. It's going to steal an electron. Instead of giving these up, it's going to take one. It's going to gain an electron. It's going to gain one from some other element somewhere when it combines. Again, we'll get into that later, but it will steal an electron. And now, if we think about fluorine had 9 protons and 9 electrons when it was neutral. 9 positive charges, and now it's gained an electron. It had 9 electrons, now it has 10 negative charges, and now the charge on the fluorine ion is now -1, right? It has an overall charge of -1 because it has one more negative charge than positive charge. Here's the way we would write that. We're going to put just a minus sign right here. We're not going to put a 1. So whenever we're writing our ions, if it's just a charge of 1, we would just put the sign. So like if it was +1, we would just put a plus instead of the 1. But anything above 1, then we start signifying what that number is, okay? Let's do a couple more examples just to make sure that we've got it. So hydrogen. Let's look at hydrogen right here. Number 1 on the periodic table. 1 proton, 1 electron. Therefore, it has 1 valence electron. It's the only electron that it has. And so for hydrogen, now hydrogen is a special case. Most of these other ones, they want 8 electrons in their outer shell. Hydrogen, it only has that 1 energy level. And remember that first energy level, it can only hold 2 anyways. It can only fit 2 electrons in that first energy level, which is the only energy level that hydrogen has. And so for hydrogen to have a full outer shell, it really just wants 1 more electron. It wants to have 2 electrons in its outer shell. Now hydrogen can kind of do both. Hydrogen, for the most part though, will lose this electron. It will get rid of this electron like magnesium does. But sometimes it will share electrons. We'll get into that again in a couple more chapters. But for right now, we're just going to say that hydrogen will lose this electron. And so when it loses that electron, it has now become H+, because it has 1 more proton than any negative charge. And so it is now positively charged. It's an H+ ion. Let's do one more. How about oxygen? Oxygen, if we look, is right here in group 16, meaning it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. For oxygen, again, it's going to be like fluorine. It's going to gain 2 electrons. It's going to gain 2 electrons. And so for oxygen has now become, since it's gained 2, is now 2-. And so I want to point something out here that's usually trips kids up, and it's this idea that they think, well, if I'm gaining electrons, then there should be a plus here because I'm gaining some, so it should be +2. But again, that plus and minus isn't about really what you're gaining or losing. It's about the charge that you've gained or lost. And so since I have more negative charge, I'm going to be negatively charged because I have more of those. I have 2 more negative charges. And same thing with this positive here. So kids sometimes think, I lost 2 electrons here, so it should be -2. But don't get caught in that trap. You've got 2 more positive charges because you lost these, so it would be 2+. So just be aware of that sometimes is trips kids up. So now, moving on from that, thinking about in terms of size. So that's what we're really looking at here, right? We're looking at the ionic radius. So we've defined what an ion is. It's whenever you gain or lose electrons and you become charged, either positive or negatively charged, right? So these are all ions right here. And for the most part, really, most elements on the periodic table, they don't really exist as just neutral atoms, you know. Most of them exist as ions, especially like all of these really reactive ones, like these alkaline and alkali metals here, and things like oxygen, fluorine, chlorine, all of these guys, they exist for the most part bonded with other things as ions. But again, we'll get into more of that later. But in general, if you lose electrons, your size is going to decrease, which makes sense, right? If magnesium loses these electrons and it no longer has that outer valence shell, right, it's going to drop down in size. But if I gain electrons, that means my size is going to increase, which again, logically makes perfect sense. So let's take a look at the patterns in the periodic table when we think about that. So we saw that with atomic radius, as I move this way across a group, size decreases. And as I move down this way, size increases. Let's think about it in terms of ions, though. Ions. Well, first let's take a step back and think about what's happening with the charge. The pattern we see here is that all the elements in group 1 here, since they have one valence electron, they are going to typically lose that one valence electron and get a charge of +1. So all of these elements in group 1 typically have a charge of +1. That means same thing for group 2 here. They have two valence electrons, and so typically they're going to lose those two valence electrons and get a charge of +2. Skipping over the transition metals like we have been doing, because again they have some different rules, but skipping over those, over here with our nonmetals, well, except for group 13 here, so I'm going to put a little line here. These guys here in group 13, remember, have three valence electrons, and so they will typically get a charge of +3. We're going to skip over group 14 because group 14, which has carbon, carbon can kind of go either way. Carbon is typically going to share electrons. I guess what we can put here is that we can put sometimes it'll be +4, sometimes it'll be -4. So we'll keep that like that. But then we get over here. Group 15, 16, and 17. Group 15 has 5 valence electrons. And so for group 15, those elements that have 5 valence electrons, like for example nitrogen, 1, 2, 3, 4, 5. Now again, it's going to be easier for nitrogen to try to gain 1, 2, 3 in order to get that full shell instead of trying to get rid of 5. So what we're going to see is that those elements in group 15 are going to gain 3 electrons, which means their charge is going to be -3 typically. And then in group 16, like which was oxygen there, we already did that example, those elements in group 16 are going to gain 2 electrons since they have 6 valence electrons, so they're going to gain 2 to get 8. So they're going to typically have a charge of -2. And then our elements here, starting with fluorine, these elements in group 17, they only need to gain 1 electron, so they typically have a charge of -1. Now, what are the charges of these guys over here? Nothing. They're not going to have a charge because remember, like we keep saying, these are the noble gases. They already have a full outer shell of 8 electrons, except for helium, right? Because hydrogen and helium are in that first energy level, and so they only need 2. But they already have a full outer shell of 8 electrons, and so they don't typically bond with anything in order to get those electrons, and so they don't normally have a charge. And so these are always just 0. So there's the first pattern that we see, is that these two groups over here, we get a +1 charge in these guys, +2 charge here, +3 charge. carbon somewhere in the middle, sometimes +4, sometimes -4. And then over here we get -3 for group 15, -2 for group 16, and -1 for group 17. This is the pattern we see there. Now, let's talk about size. Last thing. When we're thinking about the sizes, okay, sizes of ions. Now let's think about this. As we move from, we'll say across a period first. So let's say period 1 moving across this way. The size, or the ionic radius, right? Ionic radius, which is the size of these ions, as we move this way, is the size of those ions going to increase, or is it going to decrease as we move across this way? Well, let's think about it. We said up here that in general, if electrons are lost, the size is going to decrease. And if electrons are gained, the size is going to increase. Well, let's look at if I move across from, if I start at period 2 here, and I move from group 1 to group 2, going this way, and then to group 13. As I'm moving this way, I'm losing more and more electrons, right? Group 1 only loses 1 electron. Group 2 loses 2 electrons. Group 13 loses 3 electrons. And so the more electrons that I lose, the size is going to decrease, right? So as I move across this way, the ionic radius is going to decrease. But now here's the thing. Once I hit this spot here, right, then I start to hit these non-metals, which are actually gaining electrons. So really, we got to think about it like this. I should have not erased that line right there. The ionic radius of the positive ions is going to decrease as I move here. But then I'm going to hit these nonmetals, okay? And so the trend going across these nonmetals here, the ionic radius of these negative ions, what is the size of these going to do? So we're starting at -3, then going to -2, -1. So that means, right, group 15, they are gaining 3. These guys are gaining 2 and then gaining 1. And so we would see that the size of these also decreases. So these decrease as well, right? Because this guy has to gain, nitrogen here has to gain 3 electrons. Oxygen only needs to gain 2. Fluorine needs to gain 1. The more electrons that I've gained, the bigger the size, right? So as I move this way, it decreases as well. But the thing is, what we would actually see, right? So these, like nitrogen and oxygen and fluorine, their ions are way bigger than the ions of these metal ones over here. So really it would be, they are decreasing, but we want to understand that like these sizes here would decrease, but then you'd hit nitrogen, which would jump way back up to a big size, but then it would start to decrease again as you move across this way. So in general, it decreases as we're moving this way. But just understanding that those negative ones are all bigger than these metal ones, basically. And then moving down this way. So if we're moving down a group, what is the size going to do there? So we're decreasing in size this way. We would actually increase in size for our ions going this way. Because, again, those energy levels are getting further and further away from the nucleus, just like we were talking about before. And so that same pattern still holds true here, that the ion size still gets bigger and bigger as we move this way down the periodic table, but the sizes of ions going this way would actually decrease moving from left to right.